Since the early days of modern seismology, geophysicists have been interested in characterizing the seismic source and determining source parameters such as time, location, mechanism, and the rupture process. Now, there are two basic approaches for determining these parameters. In the first approach, which is an inversion approach, we try to find a source that could correctly account for the kinematics or dynamics of the first arrival energy, or more recently, for the full waveform of the data that is recorded in the field. In the second approach, that we try to directly go about imaging the source. And these techniques are generally based on the time reversal invariance of the wave operator. For example, in the method that Johannes presented yesterday and today, he tries to work on the individual signals injected by each receiver in order to flatten their spectrum and ultimately get an improved temporal focus. And he gets some spatial focus as a side product. In the other hand, in the Backus and Gilbert method that I presented yesterday, we work on the arrays as a whole unit and try to optimize the signals injected by each receiver with respect to the signals injected by all other receivers in the array in order to achieve an optimal focus or image of the source. Now, yesterday I presented the method for acoustic media, and today I want to generalize the method for application in elastic media so that we can use it in real source imaging applications. However, before that, I want to revisit the time reversal process so that I can explain what the problem is and we know what to expect. So imagine we have an elastic medium with known properties, and that somewhere in this medium we have a source which is described by a moment tensor M. Now, M is a general moment tensor. However, in this talk, for the sake of illustration, I'm going to assume that the source has a double couple mechanism. Now, we know from the theory of seismology that such a source would emit energy in characteristic radiation pattern, the four-lobe radiation pattern associated with the P and S waves. And in practice, we can separate this P and S wave radiation patterns by taking the divergence and the curl of the vector displacement field. Now, going back to our experiment, the source would generate energy, and this energy will be sampled by the multi-component receivers represented by the white diamonds as data, and we take this data, we time reverse them, and we inject them back into the medium, and the new wave field will be generated, and it will eventually collapse and focus to generate the source image. And we can see that these images match our expectation by having the four-lobe radiation patterns for the P and S waves. However, the situation would be different if we repeat this experiment, this time with incomplete acquisition. For example, if I just keep 6 receivers in top right and repeat the source imaging experiment, what we would get is something like this. And to see better, I'm going to zoom into this white square and blow up the image. And we see that we have lost the radiation pattern and the lobes. And I remind you that in a perfect situation, the perfect image would look something like this. So this is the image we would get from a time reversal with full aperture, and I'm going to refer to this image as the true image. So we have a problem with incomplete acquisition, and we need to do something about it. And the solution that we provide to this problem is the Backus and Gilbert method in elastic media. Now, to start to explain how the method works, let us assume that we have a medium with known properties. This is an elastic medium. And that in this medium we have N, capital N, multi-component receivers. And these receivers start recording at time 0 and they stop recording at time capital T. Now assume that at some time between 0 and T, a source with an unknown moment tensor M and with happens at an unknown location C. And this source generates energy as a wave field, which I represent by U. So U represents the source wave field. And this source wave field will be sampled by receivers as data, D with superscript I. And I represents the receiver number. So in this talk, all superscripts will refer to the receiver number. Now each data is a vector with 3 components, where the components of the data are defined by the expression shown below here, where N, the index, represents the component and varies between 1 and 3, and therefore each data component can be expressed as the convolution of the moment tensor and the derivative of the green tensor associated with the source. Now what we would like to find are the signals A, I of t that upon injection create a source wave field psi that will collapse and eventually focus to the correct source image. And here I'm assuming the same optimization window W which I introduced yesterday. The size of this optimization window should ideally be 2 to 3 times of the dominant wavelength in the experiment. Now the source wave field psi can be expressed as the convolution of the green tensors associated with each receiver and the optimized signals that we want to find, as shown by the expression shown here. And to achieve the goal, that is to design psi such that it will collapse to the correct source image, we define an objective function with this form, where we are minimizing the difference between the injected wave field psi and the product of a constant c, which I'm going to return to shortly, and f, which is the equivalent body force associated with our source. Aki and Richards define this equivalent body force with the equation shown here, where m is the moment tensor and delta is a Dirac delta function. Going back to our objective function, you might be wondering that psi is a displacement field and f is a force and the units don't match. The reason we can write this objective function as shown here is that, as we show in the paper, the source wave field U at the time of the source and in the areas near the source is proportional to the source force F, and we are taking the proportionality constant C to be unity with dimensions of displacement over force. And that is why we can legitimately write our objective function with this form. Now this objective function is in the time domain, and we can now transform it to frequency domain through a Fourier transform and write it for each frequency component separately as the one shown as the objective function shown here. And this is the objective function that we need to minimize for each frequency independently in order to solve our optimization problem. This minimization will result in a system of linear equations which is shown here, and for the detail you can refer to the paper. Here the matrix on the left is a 3n by 3n matrix, which is comprised of 9 submatrices, which I represent by gamma sub KL. And each of these submatrices is defined by its element I and j as the integral shown here, where we are integrating the product of the 2 Green's functions associated with the receivers I and j, and the integration is carried out over the optimization area W. And note that we are assuming, or we are implying the summation over the repeated index R here. The important thing here is that as long as we know the medium, we could compute the green tensors associated with each receiver, and therefore we could compute this integral. And by that, I mean that the matrix on the left can be computed, and therefore it's known. The matrix on the right is a 3n by 1 vector, which is expressed as the expression shown here, as a product of the moment tensor of the source M and the derivative of the green tensor. And even though this expression contains the unknown information about the source, such as the moment tensor and xi, the location, we don't need to know these parameters explicitly, because the whole expression on the right is indeed the frequency components of the data that we record in the field. Therefore, as long as we have the data, all the information about the source that we need is encoded in the data. And therefore, the right-hand side of the system of equation is also known. And all is left is a 3n by 1 vector of the unknowns. In short, if I represent the matrix on the left by gamma and the vector of unknowns by A and the data vector by D, I'll end up with a compact system of equations as shown here, which is exactly similar to the equation that I showed yesterday in the acoustic talk. And therefore, all we need to do is to solve this equation for the unknown coefficients A of omega for each frequency. And in the last step, we do an inverse Fourier transform for take these frequency coefficients back to the time domain to create the time signals that we need to inject. We inject these signals, and an optimized wave field psi will be created, and we need to scan this optimized wave field psi within the optimization window W in order to locate the source and obtain the source image. Now I've done this experiment for you, and I'm going to just show you the signals computed for the vertical component of receiver number 4 as an example. Here on the left, we see the time reverse data recorded by the vertical component of receiver number 4. And we see that this signal contains the direct energy associated with P and S waves, indicated by P and S letters. And it also has an event associated with the reflection energy, indicated by letter R. On the right, we see the same signal, or a corresponding signal for the same vertical component of receiver number 4, computed with the Backus and Gilbert method. As we see, this signal is different from the time reverse data in both amplitude and shape. And in particular, note how the weak reflection energy in the time reverse data is boosted and amplified in the Backus and Gilbert trace. And such differences will be responsible for the improvement that we get in the source image that I'm going to just show to you. Here, I'm going back to the time reversal image that I showed you earlier. And finally, I can compare this with the Backus and Gilbert image. So this is time reversal, this is Backus and Gilbert. Time reversal and Backus and Gilbert. And to see the improvement better, I'm going to compare this Backus and Gilbert image with the true image as we compute with the complete aperture time reversal. Now look at the left panel and focus on the positive and negative lobes in the true image and compare this with the Backus and Gilbert and the time reversal. Now look at the right panel and see how the orientation of the S-wave image is better resolved in the Backus and Gilbert image as compared to the true image. So we have some significant improvement. I'm going to show you one more example, and this time I'm going to show you a different configuration of receivers in order to show you how sampling our wave field differently would have a great effect on the source image. So I repeat the time reversal and Backus and Gilbert experiment with this configuration, and here I show you the time reversal image. We see that the time reversal does already a great job in creating the S-wave image, but it's not as impressive in the P-wave image. And now I can compare this with the Backus and Gilbert image. So once again, time reversal and Backus and Gilbert image. And again, we can compare this with the true image. So true, Backus and Gilbert, time reversal. Backus and Gilbert, and true. So you might be thinking, what's the big deal? Because the image that we get from the time reversal is already doing a good job in resolving the S-wave image. And this S-wave image is enough for us to deduce the mechanism of the source. But I want to remind you that here we are dealing with a simple 2D example where with just 6 receivers we are sampling a good portion of the wave field. But this is not possible in the 3-dimensional experiments. And my point is that in general, the advantages of the Backus and Gilbert method over time reversal would be more pronounced in the 3-dimensional world. And finally, before finishing the talk, I would like to say a few words about the structure of the gamma matrix and define what each element of this matrix does, so that we can have more freedom and flexibility in customizing the method for specific situations. The gamma in general has 9 submatrices, but by definition, gamma is a Hermitian matrix, so it has Hermitian symmetry. That means whatever function we attribute to the subdiagonal submatrices, this same function could be attributed to the superdiagonal submatrices. So we are left with 6 submatrices, out of which the 3 diagonal submatrices are responsible for determining the relationship between the same component of different receivers. For example, gamma 3,3 determines the weights between the third component of a generic receiver I with the third component of all other receivers J. The subdiagonal submatrices are responsible for determining the way different components of different receivers work with each other to achieve the best focus. For example, gamma 3,2 determines the weight between the third component of a receiver I with the second component of other receivers J. With this background, if we go back to the system of equations, we can see that we are able to readily modify this system for situations where we have 2 components, or we have 3 components and we don't want to use the third one. In which case, all we need to do is to ignore the parts that contain the third component and get a 2D version of the linear system. And similarly, we can modify this to get a 1D version of the linear system, as the equation shown here. And this equation is exactly similar to the equation I showed to you yesterday in the acoustic case, where we had just 1 pressure component. Finally, yesterday in the acoustic talk, I talked about the connection between the time reversal and the Backus and Gilbert method, and I said that the Backus and Gilbert is a more general theory than the time reversal. And here I want to say that the same connection holds true here. And to see that, let us crudely approximate the gamma matrix on the left by an identity matrix. And this is equivalent of ignoring all the crosstalk between different receivers and the different component of different receivers. And in that case, we get a system of linear equations which is in the frequency domain and expressed as the one shown here. Now, note that the complex conjugation on the right in the frequency domain corresponds to the time reversal in the time domain. So that if I do an inverse Fourier transform on this system, I get an equation which exactly describes the time reversal process. So again, we can see that the time reversal is just a special case of the more general Backus and Gilbert focusing theory. In the end, I would like to summarize the talk by saying that we have a formalism which is simple and general enough to be applicable equally in the acoustic and elastic media. The purpose of the method is to mitigate the adverse effect of incomplete acquisition and the time reversal focusing. To use the method, we only need to know two pieces of information. First, we need to know the elastic properties of the medium. And second, we need to have an estimate of the source location, and this is needed to define the optimization window W. And apart from these two information, we don't need to make any other assumption. The method can find application in source imaging in both exploration and global scales. In the end, I would like to thank my colleagues Oscar, Esteban, Yuting, and Elias, and also thank John Scheimer from Shell for his insightful advice. Thank you very much, and I'll take questions.